Today we'll understand how differentiation is done by computer program by using Python code. Now to understand that code, first we need to know some fundamentals of differentiation. Now let's first understand what is differentiation. So differentiation is nothing but how the function value, that is y, is different from x. So that differentiation, that DIFF, difference, that term comes from difference. How y is different from x means how y is going to change if x is changed. For a given expression, any expression, let's say for example y equal to fx, if you change this x value, how the y is going to change? So that's the question, and the rate at what the y is going to change is the differentiation. Now when we do differentiation of an expression and we get a expression of after differentiation, that expression gives a general representation of how the function is going to change at a different x value. Okay. Now if let's say for a differentiation at a given point, let's say at x equal to x0, the dy dx, we write that f prime x0, that is nothing but slope of the tangent. Let's say for this expression y equal to fx, let's say this line is representing this expression at x equal to x0, how y is changing, the function value is changing. That's the question, and that's what the differentiation gives. Now the change is represented, the slope of that tangent at that line. So if the function is changing rapidly, means y is changing rapidly, the slope at that point is going to be very high or steep. So if that slope of that tangent is tan theta, is actually the tan theta is the differentiation at that point. Okay, if the theta is an angle with a horizontal line or x-axis, then tan theta is the slope of this tangent, and the differentiation is nothing but at a given point is nothing but the tan theta value, a slope of that tangent. I think till this point things are clear.
Differentiation technique that you do in your class, like differentiation of x squared is 2x, differentiation of sine is cos x. There is other method of doing the same thing or similar thing. That's called finite difference method. So computer use this kind of method to do differentiation in general,
or to do differentiation or how the function is changing at a given point. Let's understand. So there are three different way of doing finite difference. Now they are like forward, backward, and forward, backward, and central. Let's understand what they are. So we know that this tan theta, slope of this tangent, is the differentiation of this expression at a given point of x equal to x0. So the tan theta can be written, the slope, if we make this, can take a small triangle, let's say which base length is delta x. So you know x0, you can get the value on that point, that is fx0, you can get from the expression, the equation itself. Now if you take a small step forward, the small step is delta x. Now land to a new point which is x0 plus delta x, and you evaluate the function for that point. So that can be done. So that is f of x0 plus delta x. Now we can make a triangle between this small step length. Just focus here now, just in this triangle. So the base length is delta x and the height is fx plus delta x minus fx0. You see here the horizontal line is at fx0 and this point is at fx0 plus delta x. Okay, so if this is the triangle and this purple line is a tangent, then the slope of this tangent tan theta is height by base, that is fx0 plus delta x minus fx0 divided by delta x. Now if you know the expression, then taking a sufficiently small delta x, we can evaluate the tan theta, means you can do the differentiation at a given point. So this method, this simple subtraction and division, by only doing this we can do differentiation of more or less any function with a sufficiently small delta x. Okay, so this method is called forward method of finite difference. Now there are some other variants, like instead of taking step forward you can go backward. Like if you are in fx0 and you move backward by delta x step size, so you'll be landing to a point of x0 minus delta x. So if you evaluate those numbers along the function, you'll be getting fx0 minus delta x and fx0. So again subtracting and dividing, you'll be getting slope of this line, the same like the forward method. So this method is the backward method because you're moving backward from x0 to x0 minus delta x. Now there could be a third variant of course, that's called the central. So here you take x0 where you want to know how the y is changing. So you are at point x0 and want to know how the y value is changing at this point. Now for that you can draw a tangent in such a way that the central point of that tangent is a x0, and you take a backward point x0 minus delta x by 2 and x0 plus delta x by 2 at the forward point, taking in the like the previous methods. So y value at x0 plus delta x by 2 and minus y value at x0 minus delta x minus by 2. So you can evaluate the slope by f of x0 plus delta x by 2 minus f of x0 minus delta x by 2, that is the height of this triangle, small triangle, by divided by the base, that is base length is delta x. So you can divide that, you can get the slope of this upper line, that is tan theta. So if you just calculate this expression, evaluate this expression, you can get a differentiation of more or less any expression. So in computer programming, these finite methods are used to evaluate differentiation, to do differentiation in general. Okay, so now coming back to how you will code for doing differentiation. So there are two distinct ways. So one is the evaluate the analytical expression, and another one is the calculate by finite difference method. In analytical method, let's say if you have an expression of 3x squared plus 5, you can do the differentiation in advance manually. Like differentiation of this expression gives 6x. Now if you use computer program to evaluate the 6x for a given value of x, let's say x equal to 12. So in that case, this expression will give you 6 into 12, that's equal to 72. So the slope of this function at a point of x equal to 12 is going to be 72. You can just readily evaluate this expression and get the differentiation done for this expression. So that is one way of doing differentiation using computer program. And let's see the other ways. The theory behind the other way, I have already shown you the finite difference method using forward, backward and central approach. So you can use any one of these approach at a time. So normally it has been seen that the central method gives relatively better result as compared to other method, forward backward method. So just to compare, so between the advantage and disadvantage of doing this evaluation of analytical expression and using the finite difference method, we can understand the difference very easily. Like in the advantage, in analytical expression, the result is going to be the exact value, the actual value, the slope of this expression, and definitely it's going to be quick because you'll be evaluating this expression only, and of course it is easy to do. And on the other side, if you see the finite difference method, the advantage is a kind of a generalized approach. So when you don't have any idea about how the expression is, or the expression is so complicated that you can't do manual differentiation, in that case this finite difference method will help you, because in that case you don't have to do the differentiation manually. So taking a very small step, this method like forward, backward and central method of finite difference is going to do the approximate differentiation for you. And of course this is not going to be the exact a result like the analytical method, and of course in most of the cases it may take some additional calculation and it's not as quick as the differentiation or evaluating the analytical expression. And about the disadvantage, so of course this is not this evaluating the analytical expression is not a generalized approach. When you don't have any idea about this expression, in that case will not be able to do this method. Now in context of machine learning, when you have the hypothesis function given, so and it is a very simpler expression, in that case of course you can do manual differentiation in advance and you can just evaluate the expression. So that's why I am talking about this method here. You see, in some basic machine learning method, you know the hypothesis function in advance and you can do the differentiation by hand. So only by evaluating one expression you can get the slope of that function. So that's the point why I'm talking about this thing here. And for the other cases where you don't have any idea about the expression, how is going to do the expression, and it's very difficult to differentiate manually, in those cases you will be using finite difference method and will go with the approximation. And the other disadvantage of this finite difference method is the result is very much dependent on the value of delta x up to certain limit. Means what I mean to say, if the delta x is sufficiently large, so it will impact very much on your result. But if it is sufficiently small or smaller than a specific number for a specific case, it's not going to impact your result that much. It will going to vary the computation cost. Okay, so now I think the basic is clear about the differentiation. So I'll share this diagram in the description section. Let's move to the coding part, and there will be understand how the code is working. For coding, we'll be using a Kaggle online code editor. So now I am in the Kaggle editor page. You can use Jupyter also, but using Kaggle save you lots of time of installing etc. in that complexity. So you can just come here and log in Kaggle and do coding in Python. So now let's see what this program is doing. Here I have written a function named the numerical slope. So you know the differentiation is nothing but slope. So the function name is numerical slope. So it will evaluate the numerical differentiation value and will return it. So how it is doing, we'll explain. And the second one is the analytical slope. So it will evaluate the analytical expression and will return the value. Not just from the bird's eye view, you just see how small this function is. It's nothing, it's just returning the value of the function of a function. Okay, and on the other hand, you see the numerical method, the length of the code, and of course some calculation is involved, and here you don't have anything. But the advantage of this numerical slope is that with the demonstration will show you that it can more or less evaluate any expression with certain accuracy, but this analytical method is entirely limited to this expression only. Okay, now so I'll run this code. So before that, so these are the functions to do my numerical and analytical calculation, and here is the function that need to be differentiated. So it's called lambda function. I'm using the lambda feature of Python. The actual expression is this one, this x square plus 5. I just want to evaluate this x square plus 5 at a point of 3 by using numerical method and as well as analytical method. Now if I run this code, so now I have run this code and see the result. Here the numerical method is giving result of 5.99899, which is more or less 6 only, and the analytical method is giving the exact result of 6. And we know that the differentiation of this function at the point 3 is going to give you the result 6 because it is 2x. So 2x is 2 into 3 is 6. Now what if I change this expression a little bit? Let's say I make it x cube plus 5 and I run this expression. So what will happen? Yeah, see here. So the analytical method is giving the result of 6 only because I haven't changed this differentiation. So every time I change this the main expression, the main function fx, I have to manually do differentiation and I have to change the expression here. Then only this analytical method will be going to work. But the numerical method is going to work even after changing this expression. So this x cube plus 5 differentiation, this expression is going to give you 3x square. We know that. And the 3x square at 3 gives 3 square 9 multiplied by 3, that is 27. You see here, this number 26.99, this is not exactly 27, but it's pretty near to the value of 27. So the point is now clear, no? The numerical method is giving result for a general expression, like for most of the expression you can give, but analytical method you have to do this differentiation manually and feed into the program. Okay, so till this point I think things are clear. Now see how this forward, backward and central methods are, what are they doing. Okay, now in forward you see I'm just taking 2 points. You have the initial point, and initial point plus step is the final point. So I've explained the theory, and the same way the backward point and the central point. The same calculation is doing here as I explained in the basic part. And based on that final and initial point, I'm just calculating the slope and returning that slope, and that slope is getting represented here as a result. Okay, just to have a fun, let's say some other expression. Let's say x to the power 4 plus 5. So is it able to do it? Yeah. Let's check. So the actual differentiation of this expression is going to be x to the power 4 plus 5 is the differentiation is 4x cube at point 3. So 3 cube is 27. 27 multiplied by 4 is 108. Okay, you see the result is 107.94. Okay, now if you ask me how these functions are working, so now focus. So I'll spend a few minutes to explain how this numerical slope, this function call is working. So it's a print statement in Python syntax. So the actual evaluation is starting from here, the function evaluation. It's calling the numerical slope function from here, this numerical slope function, and casting this function. This function is this variable, this expression x to the power 4 plus 5. So this x to the power 4 plus 5 is going into this function variable, and this function call is passing that expression x to the power 4 plus 5 through this function to here, this fun, the short of this function, short form of, and also passing this point 3 from here to the initial point. Okay, so just let me mark it for you. This expression is going to this function, and this function is going through here. From here it goes there, while I'm calling this numerical slope function. Okay, so through fun it is coming in 2 different locations, here and here. So finally, when I'm asking this fun at final, it is evaluating this expression only, x to the power 4 plus 5, and in final point minus x to the power 4 plus 5 at initial point. Okay, and see for other variable, this 3 since this is the second variable, so this is getting passed to this initial point, and all other necessary points are as a default value. These things, the step size and the slope type means it's going to be backward, forward, or central. Okay, now what happens if I change this backward to, let's say, central? So right now my result is 107.94. Let's make it central. So if I change it to central and execute, you see the result. So it was 107.94 99. So now it's exactly 108.00000 etc. Okay, so now here you can see the central methods of this finite difference gives a relatively better result as compared to the other methods. Now how the step size impacts, let's change it. Let's now, right now it is 0.001. If we change it to 0.1, what will happen? You'll see some additional error, small error is getting incorporated here, 108.03. Even though it's small, but it's a little bit larger as compared to this thing. This 108.5 times 0 to mean. Okay, so excellent result. I think to this point it's clear. I think now you know how to do differentiation using a Python code. So I've shown you both the numerical way and the analytical way. And remember, both these things are important in machine learning. None of these is superior as compared to others. So each having some benefit and each having some disadvantage. So you are watching Devar Lab, and if you like this video, please subscribe my channel and give a thumbs up to this video. Thank you.